Hello and welcome to York Universe, the astronomy and astrophysics radio podcast, written and presented by the students, faculty, alumni, and friends of York University. You'll now find us wherever podcasts are distributed. I'm Sana Withers. I'll be one of your hosts this evening, and I'm joined by Julie Tomei. We're broadcasting live from the Allan Carswell Observatory located at York University in Toronto, Ontario, Canada. York Universe broadcasts live every Monday night at 9 p.m. local Toronto time, or currently Tuesday morning at 1 a.m. Universal time on YouTube at York U Observatory. We also run in concert with our online public viewing team run by the observatory staff. To navigate to our live show or to find out more about us, please check out our website at yorku.ca/science/observatory and follow the links to our online public viewing chat on YouTube. For any questions or comments you may have on past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can also always connect with us on Instagram with the handle @YorkUObservatory or on Facebook at Allan I. Carswell Obs. All of our programs are free, but if you would like to make a donation, please see our website at yorku.ca/science/observatory. We will be monitoring the chat room on YouTube for questions and to post content, but unfortunately, we won't be able to bring you any live images tonight because the weather is terrible, as it usually is at this time of year.
Yes, definitely colder than I would like and cloudier than I would like.
Yeah, it's that weird time, like, where the weather just can't decide what it wants to do.
Yes.
It's just,
Uh,
yeah,
is it raining? Is it snowing? Is it freezing rain?
yeah, I'm guessing you got freezing rain the other night too, because we had freezing rain in Aurora.
Yes. But I was not at home, so I was south enough to not be where there was freezing rain.
Mm. Yeah, my backyard looked very pretty with the freezing rain, but I was definitely glad not to be out and actually commuting in the freezing rain.
Oh yeah.
Yeah, but I guess this is a good time for data processing and looking at archival pictures like are being posted on the OPV.
Yes, they're definitely very beautiful pictures.
Mhm. Yeah. Well, to start us off, we've got a full show for tonight, and Julie, you're first up in this week in space and astronomy history.
Yeah, so we're going to start by going back to April 5th, 1990, with the first launch of the Pegasus rocket. The Pegasus is an air-launched multi-stage rocket. So in other words, it gets attached to the belly of a plane and it launches once the plane is at about 12,000 meters in altitude, the 39,000 feet. For those of you who are more imperially inclined, it was developed by Orbital Sciences Corporation, or OSC, and built and launched by Northrop Grumman. It was the world's first privately developed orbital launch vehicle. It carries small payloads up to 443 kilograms into low Earth orbit. It's made up of 3 solid propellant stages with an optional monopropellant fourth stage, and was started. The development started in the spring of 1987, and was funded by Orbital Services Corporation and Hercules Aerospace. Government funding came into play when there to support operational testing, and NASA provided a B-52 airplane with cost reimbursement for captive carry tests in the first few flights. The anchor customers for this private venture were Orbcom Communications and OrbView observation satellites. And the first flight, as I said, was April 5th, 1990. And the aircraft was being piloted by NASA test pilot and former astronaut Gordon Fullerton. By 1994, the launches were done using the OSC's L-1011 plane called Stargazer, which is a converted airliner formerly owned by Air Canada. Stargazer is a reference to Star Trek The Next Generation, where Picard captained a ship called Stargazer and Riker once served on a ship called Pegasus. The first flight had a payload of a spacecraft called PegSat, and NavySat. So PegSat had the primary objective to obtain environmental data from the Pegasus vehicle to use in future development. And it deployed the NavySat and conducted scientific experiments over northern Canada to support the CRRES mission, which is the Combined Release and Radiation Effects Satellite, which was launched July 25th later that year. And that mission investigated fields and plasmas and energetic particles inside Earth's magnetosphere. Standard Pegasus rocket has been discontinued, but the Pegasus XL is still available. And the Pegasus was used to conduct 45 missions, launching nearly 100 satellites.
I gotta say, missions like this are really cool. Like the idea of just like sticking a rocket on the belly of a plane and launching it from the air is just awesome.
I want to know who thought of that.
Yeah. Yeah,
If we get it that much higher, we can do this.
yeah, it's kind of the same with like what was it, the 747 that flew the space shuttle around?
Yes.
Like, who came up with that idea and what looks did they get from people?
I know. We'll just attach things to airplanes.
Yeah.
The very first space shuttle that was called Endeavour and never went to space. It was like for testing. It was strapped or attached or whatever to an airplane for that.
Mm-hmm.
So it was kind of going back to that first thing to deliver the space shuttles to their museum homes.
Mm-hmm. Yeah, I love the 747, so it's really cool to see the awesome space shuttle attached to the awesome 747. But
Right?
it's really an interesting launch idea. I'd really love to see one of these launches. I've seen kind of a couple of them on video, but I feel like this would be a really cool one to watch, but you'd have to be like in an airplane nearby the launch happening, is my guess. To actually,
Probably.
yeah.
Yeah, because I mean, 12,000 meters is pretty high up there.
Mm-hmm.
But I would love to see any launch. I have not seen in person anyway. I've seen plenty of them on screens, but it'd be really neat to get to see some in person.
Oh yeah. Oh yeah. The thing I really want to see is a night launch.
Oh yeah,
Those look gorgeous.
yeah,
So we'll need to make my way down to, what is it, Florida, where they do a lot of the launches at some point,
yeah.
but see a launch. But yeah.
One day we'll add it to the list of things, places to go and things to see.
Yeah. Yeah. Observatory trip, maybe at some point.
Nice. We'll call it team building.
Yes, I agree. And maybe we'll get the university to pay because it's team building. But speaking of launches, I'm talking about next the launch of the Pioneer 11 spacecraft, which happened on April 6th, 1973. Now, Pioneer 11 was part of the like twin missions, Pioneer 10 and 11, that were launched by NASA in the 1970s with the goal of exploring the outer solar system. So before Pioneer 10 and 11, we'd only ever kind of seen up close the planets in the inner solar system, kind of only really gone out to Mars. And as we've really learned over the years in space exploration, if you really want to understand a planet or something in our solar system, the best way to do it is to actually just go up to it and investigate it with a spacecraft, either through flybys or orbiters or even sample return missions in some cases. Telescopes can only get you so much in terms of understanding these things, so you really need to go to them in person to understand them, which was the point of the Pioneer 10 and 11 missions. Not only that, but they also, it kind of seems like they were providing some sort of experiments for the later Voyager missions that NASA would launch later. In particular, seeing whether or not spacecraft could actually pass through the asteroid belt. So this is just kind of like a little cloud of asteroids that's between Mars and Jupiter. And we now know that the asteroid belt is not very dense. There's a lot of kind of open space in between all of the asteroids in the asteroid belt. But thinking back to the 1970s, when nobody had ever sent anything through the asteroid belt, it was still kind of an open question of, can we send spacecraft to investigate the outer planets hands-on and actually have them make it through the asteroid belt? So that was also one of the goals of the Pioneer 10 and 11 missions, is to see whether or not you could safely pass through that asteroid belt as a sort of pathfinder for the Voyager missions to come later. Now, like a lot of the early missions that NASA launched, they tended to do things in twos. So there were the Pioneer 10 and 11 spacecraft that were sister spacecraft, and the Voyager 1 and 2 spacecraft that were also very similar. In 1972, they launched the Pioneer 10 spacecraft, which was the first one to actually venture outside of the asteroid belt and get up close and personal with the planet Jupiter. But then a year later, in 1973, they launched the Pioneer 11 spacecraft. And even though it wasn't the first to venture to that part of our solar system, it was still the first mission to actually go to Saturn, since Pioneer 10, I don't think, visited Saturn, or if it did, it visited after Pioneer 11. Now, there were lots of interesting things that Pioneer 10 or Pioneer 11 showed us when it went to Saturn, which includes providing the first conclusive evidence that there is a magnetic field at Saturn. It also showed that the atmosphere of Saturn is made of mostly hydrogen. It also took several sets of observations on moons of Saturn, including Titan, which we now know that Titan is like a very complex and dynamic and very, very interesting world that's definitely worthy of exploring. But just based off of the instruments that were available to the Pioneer 11 spacecraft, it really just looked like this orange fuzzy ball that was also very cold, having a temperature of around minus 193 degrees Celsius. On top of studying Titan, it also discovered 2 new moons of Saturn and discovered a new ring at Saturn called the F ring. Most of the rings of Saturn are, very big and bright and obvious, at least when viewed at the right angle. But the F ring, in contrast to that, is this very narrow and sort of thin and faint ring that's pretty far away from Saturn and its closest ring, the A ring. So to discover the rings like the F ring, it's really important to actually go out to Saturn and get that sort of hands-on experience, I guess is one way to say it, to be able to discover these new things. Before visiting Saturn, though, Pioneer 11 also visited Jupiter. It did a flyby of both of the planets, which became the second ever probe to visit Jupiter after Pioneer 10. It found some interesting things there as well, which included returning pictures of the polar regions of Jupiter for the first time, taking the most detailed images of the Great Red Spot ever, and also studied several moons of Jupiter. Now, like a lot of NASA missions, they have a promise of what was it? They under promise and over deliver is, I think, the right way to say it. So even though it wasn't really meant to last for an insanely long time after doing its main science mission, it continued working for almost 20 years after launch until 1995. It wasn't sending science data towards the Earth the entire time. This was partly to preserve power, and also because it was a very long time. The systems were kind of starting to deteriorate. So it was only transmitting engineering data back to Earth by the time that it died in 1995. And it is no longer in contact with the Earth, unfortunately, but it is actually one of only 5 spacecraft to this day which are on a trajectory out of our solar system. So a very, very interesting mission, one of the early missions, early NASA missions, that was really influential to our understanding of the solar system.
Neat. I didn't realize how big a concern the asteroid belt was. I know that we tend to maybe overpopulate it when we have representations of the solar system. But I didn't realize it was such a big question of whether or not it was possible to get to the other side.
Yeah, there's a couple of things like that they feel like just sort of common sense in a way now. Like whenever I think of the asteroid belt, I know there's a lot of asteroids, but I also know there's a whole lot of space there. So obviously it's not a concern, but it's I think kind of similar to the early days of spaceflight, where people didn't know whether or not astronauts would be able to swallow, for example, when they were in space, because they didn't know whether or not it was gravity that was helping to swallow food or if it was muscles within the neck. And, it was one of the things that was very quickly discovered when astronauts went into space and discovered that they could still swallow in 0 Gs. But it's kind of interesting the things that you learn in like the early days of space exploration that now have just been like, no one thinks about it. It's kind of common knowledge at this point.
Yeah, taken for granted.
Yeah, yeah. That's a good way of putting it. Really taken for granted now.
Yeah. Um, I just love how like wherever you go around Saturn, you discover new moons.
Oh my God, the 200 moons now that were recently discovered.
Right? When I'm teaching, I love telling kids like, so when I was your age, we knew about 21. I
It's
can I can tell how old astronomy books are by their Saturn moon data and their status of Pluto data.
yeah. It's still kind of surprising to me that Saturn actually has more moons than Jupiter that we know of, at least. I don't know. I always just thought of, Jupiter having the most moons, and that just kind of made sense. But now Saturn is really putting it to shame. Like,
Well, maybe it's not a competition. Um,
yeah.
I there's like a little cartoon that I saw that was like Mars and Earth and Mars saying, "So, are you going to have another?" And like Mars is holding two moons and the Earth is holding one, and it's like, "No, I don't want to end up like Jupiter."
Yeah, I think I know the one you're talking about, and Jupiter is just sort of looking exhausted.
Hmm.
Yeah. Yeah, we need to update that to be Saturn now. Well, we have a lot of launches on the schedule tonight, actually, because you have another launch for us coming up next too.
Yeah. So we're going back to 1998, April 2nd. So tomorrow, but in 1998. And this was the launch of the TRACE satellite, TRACE standing for Transition Region and Coronal Explorer, also known as Explorer 73 or SMEX-4. And it was a NASA heliophysics and solar observatory. It links to my first story because it was launched on a Pegasus rocket. It investigated the connections between fine scale magnetic fields and associated plasma structures through high res photos and observations of the photosphere, the transition region, and the outer corona. So the outer layers or the upper atmosphere of the sun, if you will. It was the third spacecraft in the Small Explorer program, and it examined these structures in 3 dimensions. So the three-dimensional structure that emerges through the sun's photosphere, and also define the geometry and dynamics of the upper solar atmosphere. Its objectives were to follow the evolution of magnetic field structure from the interior to the corona, to investigate mechanisms of heating the outer atmosphere and find out what triggers and onsets solar flares and mass ejections. Trace used a 30 centimeter Cassegrain telescope and CCD combination with several filters to image the sun, which just feels like what we used to use at the observatory in those days. The exposures ranged between 2 milliseconds and 260 seconds. Trace data were used to determine the rate at which magnetic topology changes and the nature of local magnetic restructuring and reconnection processes. It was the first mission that imaged an entire solar cycle and observed some fine scale structures for the first time, such as coronal or solar moss, which is a sponge like structure at the base of coronal loops. And it took its last science image in 12 years later, June 21st of 2010. And I am going to go share in the chat a video that I found of coronal rain and solar moss. It's kind of well named.
Yeah, the sun is really cool to observe.
Yes. So many, like you think, big ball in the sky. But there's so many, like all the cells and all the convection and all that. Like there's so much structure in there.
Mhm. Yeah, I know sometimes when we've been observing the sun during solar minimum with the kind of uh the sort of neutral density filters that we commonly use to observe the sun, it just kind of looks like a big orange ball. But yeah, when you put the right filter on it, you can really see a whole bunch of these like amazing features of the sun that are just so amazing to see. And it's really wild to think of like the scale of what's going on. It might look pretty small in the sky, but a lot of these structures are bigger than the Earth.
Yeah. Um, it's funny how the earth feels big because we're on it. Um, but it's kind of tiny compared to the sun. And I mean the sun's not exactly big either. Um, Scale, man.
Yeah. Yeah, this is actually reminding me of a comic that I saw that is actually on my office door about like scales in astronomy, and you get suspicious when you see a normal number like 65 kilometers an hour when you're in astronomy. Because everything has to be some like weirdly incomprehensible unit of either incredibly small or very massive.
Yeah, 65 kilometers an hour. I must have made a mistake.
Yeah.
Let's rerun that math.
Yeah.
We used to joke like if we got something wrong, it's like, yeah, I was within an order of magnitude. It's fine.
Well, like in a lot of areas of astronomy, that's actually kind of true. Order of magnitude, correct, you're fine. Especially when you plot things in logarithms on plots, if you're within the order of magnitude, it's pretty much fine. And I probably should not be saying that on a public radio broadcast, but it's
Fine. We're just kidding.
yeah. Um, but now I feel bad for picking a non-launch related history item, but this does tie into a news item I'm going to be talking about a little bit later. So I figured it worked kind of well on that front. But we're going to April 5th, 1935, which was when English astronomer and astrophysicist Donald Lyndon Bell was born. So he was born in Dover Castle, which is located in Dover, Kent, England, to his parents Lachlan Arthur Lyndon Bell and Monica Rose Thring, I think is how you say her last name. But this astronomer did a whole lot of influential work in the field of astronomy that I didn't even know who he was. I hadn't heard his name up until I was researching him for this news item. But I think pretty much everyone who's in astronomy is at least somewhat familiar with some of the work that he's done. So that's how much important work that he did in astronomy. But just a quick couple of points about about his career. He started off his career studying math at the University of Cambridge, and then later returned to the University of Cambridge to do a PhD in theoretical astronomy. He worked at several different observatories over the years, including the Carnegie Observatory in Pasadena, California, and later at the University of Cambridge, where he was the first director of their Institute of Astronomy in 1972. But in between all of his positions, he ended up doing, like I said, a lot of very influential work. We don't have the time to talk about all of the stuff that he did, so I'm just going to kind of point out a couple of some of the maybe more famous discoveries that he made, which included in the 1980s. He was part of a study that was looking at 400 elliptical galaxies that are, on astronomical scales nearby to the Milky Way. They noticed when they were studying these 400 elliptical galaxies that they all seemed to be moving towards the constellation of Centaurus. This is definitely an odd trend, and there was a bit of discussion about whether or not they had kind of messed up their observations. But it turns out that they were discovering what's now known as the Great Attractor. This discovery and confirmation that this great attractor is actually real was only made several years after their initial discovery of the 400 elliptical galaxies. But it turns out that it's sort of the the gravitational center of the Laniakea supercluster, which contains 100,000 galaxies, including our very own Milky Way galaxy. Now, this is something that I learned about when I was in first year astronomy, just kind of Googling galaxies because they were really cool. So it's kind of interesting to know where this great attractor kind of concept came from. Now, arguably one of his most important discoveries has to do with his work on quasars. Now, quasars are these like ridiculously bright objects and these ridiculously bright galaxies that it turns out are powered by black holes. And what happens is that every massive galaxy in the universe has a supermassive black hole at the center. These supermassive black holes can have masses ranging from millions to billions of times the mass of our sun. The more massive galaxies have more massive black holes. And the quasars themselves were discovered sort of in the early 1960s and were a little bit puzzling just because of how bright they were. I guess nobody had ever really seen something like this. And it turns out that that Donald Lynden Bell was the one who suggested that black holes are powering quasars. And what's going on and why quasars look so bright in his paper, in 1969, he suggested that it's actually that these quasars are accreting matter or basically eating matter from their surroundings. And in that process, it's converting gravitational potential energy into energy that we are able to see. This is a very, very efficient process. So it's much more efficient than the more, I guess at the time you could say the more typical process of star formation that everyone would think of when they thought of galaxies. And because it's just so much more efficient than star formation, these galaxies are ridiculously bright. So when you observe quasars in the night sky, instead of observing just the galaxy, you're really observing a supermassive black hole that's in that galaxy that's accreting matter. Now, he was awarded a Kavli Prize of Astrophysics in 2008 for this discovery, along with astronomer Martin Schmidt, who was the one who first discovered quasars in the early 1960s. And one of the reasons that I say that this was arguably one of his most important discoveries is because this has really been kind of an influential idea for extragalactic astronomy and just the idea of the formation and evolution of galaxies in general. It's kind of now a well-known fact that every massive galaxy in our universe has a supermassive black hole that's associated with it. And we wouldn't have known any of this had Donald Lynden Bell not suggested the idea in 1969. So definitely a very important discovery and a happy birthday to Donald Lynden Bell.
Wow, that is definitely a lot of achievements.
Yeah, I had written some more down, but for the sake of time, we can't kind of go into all of them. But yeah, he did a lot of work in a bunch of different areas in astronomy, not just in terms of quasars or the Milky Way or the Great Attractor and the Laniakea supercluster. He discovered a lot of things about like the early stages of stellar evolution, about the Milky Way galaxy, which also included how the supermassive black hole at the center of our galaxy influences its surroundings. So definitely a lot of very interesting discoveries that Donald Lynden Bell made. And he also has a kind of documentary film that after him and some of his colleagues, they took a road trip to the Western United States to kind of, relive some of their memories when they were there. And it ended up being made into a documentary called Starmen in 2015.
Okay, putting that on the list of things to look up.
Yeah.
That sounds really cute.
Yeah. Yeah. It seems like a cute little documentary. It was him and three other astronomers, so it should be interesting.
It's
Yeah.
interesting that like I too had not come across the name, but like so many of the things he studied, so many of the things that he proposed are things that are standard fare for, undergraduate astronomy courses.
Mm-hmm. Yeah, it's like the quasars and supermassive black holes at the center of galaxies. Like, I don't really remember when I learned that, but it kind of like with the asteroid belt, this is one of those things that just kind of, I learned it one day and it just became common sense. And I don't really ever think of it, but it's just sort of like a galaxy has a supermassive black hole. I learned it at some point. don't know where it came from, but it's just like it's such a common fact at this point for extragalactic astronomy that it's interesting to know where that came from.
Yeah.
Yeah. Well, wow, we're actually on time for one in a very long time. Bang on 9:30 for our reminders. But just before we get to our reminders and a couple of interesting news items, for anyone just tuning in, you're listening to York Universe. We're broadcasting live from the Allan Carswell Observatory at York University in Toronto, Ontario, Canada. Please visit our website, yorku.ca/science/observatory to join the chat, or if you have any questions or would like to see some of our content. Tonight, you're listening to myself, Senna Withers, and Julie Tomei, and we're currently discussing some This Week in History items, mostly launches, important launches in the history of astronomy, and also important discoveries. And if you are interested in joining our online public viewing, where we're looking at some archival images, please go to our website and navigate to the online public viewing section. But we do have a couple of reminders for this week. So one reminder is that if you were looking to come by the observatory in person this week, we actually are not hosting an in-person tour this Wednesday. If you'd like to come visit us, you're going to need to wait till April 9th, which is our next in-person observatory tour. And then we're also going to be starting public tours on the Arboretum parking garage on our atrium location on the 5th floor of the Arboretum parking garage later this month on April 23rd. So we'll be running kind of alternating, or not alternating, but some atrium tours and some observatory tours starting soon. Definitely looking forward to that. We'll have some nice weather, some nice open air spaces up on the Arboretum, which is always fun. And if you're looking to do any observing this week through any potential break in the clouds, there's a couple of interesting things happening. Nothing that you really even need a telescope for this week. So starting on Tuesday, the Pleiades and the moon are going to be only a couple of degrees apart in the evening sky. The next day on Wednesday, the moon and Jupiter are going to be around 5 degrees apart, so pretty close together in the evening sky. And then Mars and the moon will be only 4 degrees apart on Saturday evening. And if you're out watching the Mars and the moon kind of get really close together in the night sky, make sure to head out around 7:20 p.m. to watch the International Space Station pass overhead. 7:20 is only an approximate time. It will vary greatly depending on where you are. So if you want to visit NASA's Spot the Station website, it will give you more specific times for when the ISS is going to come overhead at your location. But yeah, lots of interesting stuff happening in the sky this week. Don't need a telescope for any of it, although telescopes or binoculars will kind of help and make things interesting. But now we just need some clear skies, which I don't think we're going to get. But Julie, do you have any other reminders for us?
I don't. I don't know, maybe a reminder to ask the sky very nicely to clear up.
Yeah, we need to appease the sky so it will be friendly to us. We had one very nice clear night last week, and I have a feeling that we've kind of used up our luck for the next couple weeks with that.
No.
Yeah.
Well, it is as you mentioned off the top, it is that time of year.
Yeah.
Not known for its great observation conditions in Toronto anyway.
Yeah. Yeah. But we should move on to our news items. We've got a couple of very interesting news items tonight. And Julie, you're starting us off.
Yeah. So my news item is on exoplanets and a suggestion, a new method, let's say, on how to find them. So there are now several different ways of finding exoplanets: the wobble method, the transit method, the radial velocity method, gravitational microlensing. All of these, as with any method of doing anything, I suppose, have pros and cons, limitations, biases, if you will, in that certain ones will be very good at finding very large planets close to their star, and others will be better at finding smaller planets, but only if we're at the right angle to them. And so astronomers are always looking for new methods so we can get a better idea of how many planets there are out there, find some new things. get a feel for, you know, what what the universe holds, I suppose. So there's a team led by C.K. Louis, or maybe it's Louis. I say Louis because he is from the University of Paris. Um, and the team published a new method in astronomy and astrophysics recently. This method relies on detecting the magnetospheres of planets orbiting other stars. The fields can be detected using Zeeman Doppler imaging, in which the polarization of emitted light or its absorption in spectral lines is analyzed. So maybe an obvious limitation is that planets with very weak magnetic fields will not be easily detectable through this method. Another thing that needed to be addressed was that you're going to get overlapping signals from the magnetosphere of the star and the planet. So the group has developed indirect methods of detecting magnetic fields when direct measurements are challenging. So these methods include analyzing planet modulated chromospheric emission, which are variations in emissions from the chromosphere of the star influenced by the planet, observing neutral atomic hydrogen absorption during planetary transits, and examining planetary auroral radio emissions. Auroral radio emissions are produced by the cyclotron maser instability, which is plasma instability occurring when energetic electrons spiral around a magnetic field, and that emits radiation. This has been studied in our own solar system, including on Earth, and it happens along magnetic field lines. Radio emissions were first discovered around Jupiter in 1955 and provide insights into the local magnetic fields and characteristics, and that they're different across different planets. Visibility depends on an observer's position. So again, similar to the transit method limitation there. The team ran simulations on Jupiter and the Galilean moons, and the results were promising. They found that observational data over an extended time frame is needed for detecting the exoplanets, but they also found that targeted observations can enhance the potential for identifying subtle astronomical signals. With instruments like SCALO, which is an array of radio telescopes out in, I was going to say Alberta, that is not right, Australia, which we discussed in our last episode of December with our guest, Brendan O'Brien. The future is looking promising for this new method.
That's really cool. Like, that's really, really insane that you can actually detect the magnetospheres of planets outside of our solar system.
Right?
Yeah, like,
yeah, go ahead.
sorry, yeah, there was a recent JWST observation that observed aurora on Neptune. I know that magnetospheres and aurora are different, but it's just like, it's so crazy that it's kind of taken so long to really get good observations of this when it's in our solar system. So, wow, the magnetospheres of exoplanets is insane.
Yeah. What's amazing to me is that, you know, when I started my degree, you know, we were just starting. We were only a few years in to even being able to confirm that exoplanets were a thing. And in that time, we've discovered a bunch of them, like thousands of them. And so many of these techniques for observing them have been developed. You know, people trying to figure out what the atmospheres, like if there's an atmosphere, what the atmospheres are composed of around other planets. And I mean, they're all so far away.
Yeah, it's every time I read about exoplanet science, it's almost amazing to me that we're even able to do a lot of these observations in the first place. Like you mentioned the exoplanet atmospheres. I mean, think about what you have to do to measure the atmosphere of an exoplanet. You have to filter out the light from its host star, which is orders of magnitude brighter than the exoplanet itself, to actually be able to disentangle some sort of signature out of the exoplanet. It's very remarkable that we're even able to do this, like at all.
Agreed.
Yeah. Yeah, exoplanets are really cool, but I'm more of a galaxies person, but the few times that I do sort of venture on over into exoplanets, I'm always kind of amazed by it. Um, but do you know if this is like things like the transit method when you observe the planet passing in front of the star, you can kind of do that on like large fields of stars to try and pick them out. Do you know if you can do that with this method, or is it sort of you have a target in mind and you point a telescope at it and try and
I don't know. That's a great question. I the article that I read about it, the article about the article, did not mention it, but maybe there's something about it in the paper itself. Um, to be honest, a lot of things are I find amazing because I don't understand them. And I find it amazing that there are people out there who like, yeah, so we did this thing, we did a bunch of math, and look what we discovered.
yeah, I agree. I agree. It's really crazy that you can do such complicated things.
I love that there are people out there who can. I am not one of them.
Yeah, that's about how I feel about exoplanets. It's cool, but uh for somebody else to do the math and the details for. I'm very happy reading about it and talking about it on York Universe, but
Yeah.
yeah. Um, but the second news item we have is this time pivoting to galaxies. And this is, I think the exoplanet thing is super cool, and this is also super cool, which is why I'm a little annoyed that there's no articles of the articles written about this. I couldn't find any link to like Universe Today or space.com that actually talked about this. And I'm hoping that they're coming soon. They're just like waiting for comment from the astronomers who are responsible for this discovery. But it seems that we astronomers might have solved the problem of little red dots in JWST. Might have, I'm not 100% sure if the issue is settled. There's probably still some discussion and some investigating that needs to happen here, but this is definitely a really big step into understanding little red dots. So stepping back a little bit, little red dots, which I'm going to just call LRD because it's easier to say, they're kind of one of JWST's mystery objects that popped out in the data not long after the first science data was released. And they're pretty much exactly what they sound like. They're these really like small, compact objects that look like dots in JWST imaging. And the fancy way of saying that is that they're not resolved. So with other, distant galaxies in JWST imaging, you can actually see some kind of structure to them. But the LRDs, they're so small, you can't see any kind of structure to them. They're point sources. They kind of just look like stars in JWST imaging. But they have some very, very odd characteristics. One of the most striking characteristics of these things is that they are very, very red. So when astronomers found this, they decided to continue their usually terrible naming conventions and call them little red dots because that's exactly what they look like in JWST images. Now, there's been a whole bunch of energy dedicated to trying to figure out what exactly these little red dots are. I went to a conference in at the end of last year, and there was like an incredible amount of time dedicated to discussing little red dots. There's a lot of people who've kind of pivoted their research to little red dots, trying to figure out what they are. And it's been a bit of a roller coaster of exactly what's going on with these things. So you might have heard of little red dots a couple of times over the past few years because of that. But right after they were discovered, they were sort of dubbed these universe breakers. And there were some articles about how, we got cosmology wrong and a whole bunch of sort of other things because they're just that confusing. Now, basically what happened with this universe breaker thing is that when astronomers initially tried to measure the masses and the ages of the stars in these galaxies, they basically found that these galaxies are way bigger than the Milky Way. They're several times as massive as the Milky Way galaxy, which is already a decently sized galaxy to begin with. And they also contain very old populations of stars. Now, the reason that this is puzzling is because these galaxies exist less than about 1 billion years after the Big Bang. Some of them a little bit further, later on in the history, but a good number of these things were like 1 billion or so years after the Big Bang. And these types of galaxies should not have been able to form in that short of a time period. So there was a lot of questions about, why exactly do we have these galaxies that are crazy massive forming this quickly in the history of our universe, which led to the whole universe breaking title. Now, this is kind of going back a little bit to our astronomer Donald Lynden Bell, because during this whole process, somebody eventually suggested that it could just be supermassive black holes at the center of these galaxies that were accreting gas and getting very bright and kind of messing with our estimates of their masses and how old the stars in these galaxies were. This caught traction pretty quickly, and people very quickly sort of kind of jumped on the active galactic nuclei bandwagon and were like, yeah, it can't just be stars in these galaxies. There has to be something else, which is the supermassive black hole that's accreting gas and getting very, very bright. And while that did explain away some of the problems with LRDs, it didn't take away problems entirely. So, for example, little red dots, when they were studied, seem to have no X-ray emission and no radio emission. And for context, that is a very odd thing to come out of a supermassive black hole. Supermassive black holes that are accreting matter like this get very bright at all wavelengths. So they get very bright in radio wavelengths and also in X-ray wavelengths, which just isn't something that was seen with the little red dots. They also tended to have some features that looked like star formation. So certain parts of the spectrum of these galaxies looked like it was coming from stars, and certain parts of it looked like it was coming from black holes. So the overall picture was just sort of really like muddled and confusing, and there was a whole lot of like modeling and trying to understand exactly what was going on with these things. But last week, there were 3 papers that were published that seem to fix this problem entirely, which is really, really cool. So they've kind of introduced or reintroduced this concept of black hole stars. These are basically black holes that are accreting a whole lot of mass very, very quickly and kind of, I guess, looking like a star, which is why they're called black hole stars. But the thing that's unique about them and why nobody had really thought about it before is it's not just your typical black hole at the center of a galaxy. It's a black hole at the center of a galaxy that is cocooned in this really, really dense cloud of gas. And that's giving it some really weird properties. So it's able to basically reproduce some of the features of little red dots that kind of look stellar. So with these types of galaxies, you wouldn't expect them to have radiation or strong radiation in radio or X-ray, while it's also reproducing the typical classic features of black holes and active galactic nuclei systems that were kind of characteristic to LRDs. So it took a little bit to kind of come to this conclusion, but this really seems to have tied it up in like a nice little bow almost. Where it explains all of the properties, all of these weird, strange, universe-breaking properties of little red dots in just a really, really nice way. So a little bit more on what exactly we've learned about these little red dots and these cocoons of gas is that They are mostly low mass black holes. And when I say low mass, I mean they're around 100,000 times the mass of our sun to 1 million times the mass of our sun, which, believe it or not, for black holes is actually very low. Depending on the size of the galaxy, they can have masses of like a couple billion times the mass of our sun, billion with a B. So really, really insanely, unfathomably massive objects. But these ones are much lower mass, so around 100,000 to 1 million times the mass of our sun. And what's very likely going on is that these are young black holes that are accreting gas very, very quickly in this cocoon of gas. And they're probably like new black holes that are still growing very quickly, which is why we don't really see them in other places of our universe and why they were so unexpected in JWST data. All of the galaxies that we've seen with JWST, apart from LRDs, are at least somewhat similar to things that we've seen elsewhere in our universe, so kind of galaxies that are closer to us. But LRDs were really the one thing that nobody had ever seen before that just sort of jumped out. And it's because we're really seeing black holes in their kind of early stages of formation. So basically what's happening is that, yeah, again, you've got these young black holes that are accreting gas and growing, and they're just getting really ridiculously bright as they're doing that, which is why they pop out in the data so well. Another thing that could be happening with these galaxies or with these LRDs is that, it's not just the black hole in a cloud of gas, it's a black hole in a galaxy itself. So you're not only just seeing the light coming from the black hole in the cocoon, but you're also seeing the light from the galaxy. And that can kind of muddy the waters a little bit and make it even harder to kind of disentangle what's going on. But yeah, it seems that, the problem kind of looks like it's been solved. The universe is not broken. Again, there are still some details to work out. These are still just, none of these papers have been peer reviewed yet. I don't think they were just sort of published on the preprint server that everyone uses. So there's probably still a bit of work to be done here to kind of settle things and waiting for confirmation from, I guess, other people as well. But this is definitely a very, very interesting discovery. This was a really interesting set of papers that came out last week that I have been very interested in ever since. So I figured we'd talk about it on York Universe, even though there's no paper or article written about the articles yet.
Wow. Okay. So one, the universe is broken. Seems to happen frequently. I feel like everyone's like, we can't explain it. Oh, science is broken. I feel like we always end up finding an answer. So maybe people should just settle down.
No. I always see that with like people will just, exactly like you said, someone sees something that doesn't make sense and it's immediately jumping to like, cosmology is broken. We had the entire thing wrong. It's like, just no.
Just feel like if we had the entire thing wrong, it would take more than, some little red dots in a fantastic new telescope to break it.
Yeah.
Like if it were truly broken, it never would have worked in the first place.
Yeah. Like there's so many other like independent confirmations of the kind of model of cosmology and our universe that it's not broken. But isn't this wild? Like you're observing early black holes.
How far away are these things?
They're okay. I'm a terrible astronomer. Can't give you a distance in light years. They're within the first 2-ish billion years.
Okay. So very far.
Yeah.
Okay. That's so cool.
If you like redshift, they're redshift around 3 to 9.
Wow.
Which spans over 1 billion years, but the universe is 13.8 billion years old, and we're looking at things that existed in the first 1 to 2 billion years. So yeah, very, very distant, very ancient objects.
Very cool. Man, I love JWST.
Oh.
Such an amazing piece of technology.
Yeah. This is like, we were talking a little bit earlier about how it's amazing, like we can observe some of these things like exoplanet magnetospheres. And part of it is just how like amazing the engineering that went into some of these telescopes was. It's kind of incomprehensible that you can actually put this massive machine so far away from Earth and it actually works.
I'm so glad it actually works.
Oh, me too.
Would have
Very,
been
very glad.
so heartbreaking.
Oh my God, I know. I know. It would have been terrible if it hadn't worked. But yeah, it's kind of crazy because there was something like 300 individual points of failure on JWST. So any one of those 300 things didn't work perfectly, the mission wouldn't have happened. But they all worked. They all worked. We were
Yay.
discovering weird things like little red dots, and finally looks like solved the problem of little red dots, which is really awesome.
I mean, and they truly are little red dots. Like
Mhm.
I did an image search and like they look like little lights.
Yep.
They
Yep.
look like little light bulbs in space.
Yeah. One of my favorite things about little red dots and kind of other compact objects in JWST is that if you ever look at pictures from JWST, you see these like stars with spikes coming out of them,
Mm-hmm.
8 spikes. Those are the diffraction spikes, and they're just caused by the structure of the telescope itself. So different telescopes with different structures will have different shaped spikes. Like the 1 meter telescope or most telescopes that people have 4 spikes, but
Yeah.
JWST has 8 because it's just a more complex optical system, basically. But when you look at certain particularly bright LRDs, they look like snowflakes
They
because of
do.
yeah, because of the very faint diffraction spikes. They look like snowflakes, and it's just so cool.
So
Yeah.
pretty. Yeah, I've just been staring at one going, wait, but there are only 6. They look like snowflakes.
Yeah, it's because so there are 8, but 2 of them are kind of faint.
Okay.
You look at pictures of like the fainter stuff, which LRDs are, you only see 6. Snowflakey.
Oh yeah, okay.
Yeah, yeah, it's pretty cool. 6 of them come from the shape of the primary mirror,
Yeah.
hexagon shape. And then there are, I think, an additional 6 of them that come from the structure holding the secondary mirror in place, but they
Yeah.
overlap.
Yeah, yeah,
Basically.
yeah.
So it's something like that. There's NASA has like a little graphic of what causes the spikes on JWST images, but yeah, there's overlap in the spikes
Yeah.
basically.
The
But
spikes make the stars look so pretty.
I know.
It's like such an artful, like, this is what stars look like when that's not at all what they look like.
Yeah. I love them. I think it really makes the images look pretty, but I
It
know
does.
some of the people who actually work with like processing the images and making catalogs to do science with them, they all hate the spikes.
I imagine if you're doing something other than like, oh, pretty, they would be annoying.
Yeah, yeah.
But
You
that's
can,
not what I do, so I'm fine.
yeah. That's kind of what I said. Like I don't do that, so I'll just look and appreciate how pretty they are, but yeah. Well, that takes us to the end of the hour. And everyone, you've been listening to York Universe, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Julie Tomei and myself, Senna Withers. You can always connect with us on Instagram with the handle at York U Observatory and on Facebook at Allan I. Carswell Obs. You can also check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory. Thanks for tuning in to York Universe, clear skies, and have a good night.
Good night.